You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Resilience engineering is about designing systems that continue to provide acceptable service even when parts fail. In the cloud era, where distributed architectures stretch across regions, zones, and multiple providers, disruptions are not a matter of if but when. Power outages, hardware faults, software bugs, and even human errors all threaten to interrupt service. Instead of relying on luck or after-the-fact response, resilience by design embeds protective strategies into the architecture itself. This mindset shifts the conversation from avoiding every failure to gracefully handling inevitable ones. The goal is not perfection but continuity, ensuring that when a disruption occurs, the system either maintains service or degrades in a controlled and predictable way. In this sense, resilience becomes a competitive advantage, allowing organizations to maintain trust, meet commitments, and recover quickly when adversity strikes. Resilience by design is proactive, not reactive. It accepts that failures will happen and builds systems that degrade gracefully under pressure. Consider an online store during a sudden traffic surge, or a partial server outage. A fragile system might crash, locking out all customers. A resilient system, however, might continue processing orders, even if certain features, such as personalized recommendations, are temporarily unavailable. This philosophy treats resilience as an architectural property rather than an emergency fix. It requires careful thinking about dependencies, redundancy, and failover paths, so that the system bends instead of breaks. For learners, this underscores the importance of moving beyond mere uptime metrics. True resilience means building systems that sustain their essential functions, even when operating in less than ideal conditions. High availability and disaster recovery are often mentioned together but serve different purposes. High availability, or HA, focuses on minimizing downtime in the face of routine issues like server failures, software bugs, or small-scale outages. It is about ensuring services remain continuously available through redundancy and automatic failover. Disaster recovery, or DR, by contrast, prepares for larger catastrophic events such as regional power failures, natural disasters, or prolonged outages. DR strategies emphasize restoring service from backups, replicas, or alternate regions when the primary site is no longer viable. Both approaches are essential, but they operate at different scales. HA keeps the lights on day to day, while DR provides the safety net when the unthinkable happens. Together, they form the dual pillars of resilience, ensuring continuity across both expected and extreme scenarios. Understanding failure domains helps contain risks and reduce the likelihood of cascading failures. A failure domain is a set of resources that share a common risk factor, such as a physical data center, an availability zone, or even a rack of servers. If one domain fails, only the resources inside it are affected. By spreading workloads across multiple domains, organizations avoid having all eggs in one basket. For example, placing redundant instances in separate availability zones ensures that if one zone experiences an outage, the application can continue serving users from another. Cloud providers expose these domains explicitly, encouraging designs that limit correlated risk. Recognizing failure domains and planning around them is like compartmentalizing a ship. Even if one section floods, watertight bulkheads prevent the entire vessel from sinking. Redundancy models define how much extra capacity is provisioned to withstand failures. An N+1 model means one spare resource is available to take over if a primary fails. A 2N model duplicates everything, ensuring full capacity remains even if an entire set goes down. N+M models allow for multiple spares, striking a balance between cost and protection. These models are central to resilience because they quantify headroom against disruption. For example, a data center with N+1 power supplies can tolerate the loss of one unit without losing functionality. Choosing the right redundancy model depends on the workload's criticality and the organization's risk appetite. Too little redundancy leaves systems brittle, while too much wastes resources. The art of resilience is finding the balance between preparedness and efficiency. Topology choices also shape resilience strategies. Active-active configurations keep multiple systems running simultaneously, each capable of serving user traffic. This model provides both high availability and load distribution, but requires careful data synchronization. Active-passive configurations, by contrast, designate one system as primary and another as standby, ready to take over if the primary fails. Active-active resembles having two lanes open on a bridge, so traffic continues smoothly if one lane closes. Active-passive is like having a detour ready, not always in use, but available when needed. Each approach carries trade-offs. Active-active offers faster recovery but greater complexity, while active-passive is simpler but may involve downtime during failover. Choosing between them requires weighing performance expectations against operational maturity. Health checks and load balancers are the traffic directors of resilient systems. Health checks continuously probe instances to verify that they are functioning as expected. Load balancers then use this information to route traffic away from unhealthy instances and toward healthy ones. This process happens automatically and at scale, allowing services to maintain availability without human intervention. For example, if a web server crashes, the load balancer quickly removes it from rotation, ensuring users are redirected to a functioning server. Without health checks and balancing, failures could linger unnoticed, degrading performance and user experience. These mechanisms embody the principle of self-healing infrastructure, where systems detect and adapt to problems in real time. They illustrate how automation underpins resilience, transforming reactive firefighting into continuous, silent adjustment. Stateless service design simplifies failover and scaling by ensuring that no single instance holds unique session data. When services are stateless, any instance can handle any request, making it easy to add or remove resources without disrupting users. This design contrasts with stateful systems, where data tied to a specific server makes failover more complicated. Consider a stateless web application where session information is stored in a distributed cache rather than on individual servers. If one server fails, another can immediately pick up the workload. Statelessness thus enables elasticity, resilience, and simplicity, though it requires careful planning of where and how to store state externally. It demonstrates the broader lesson that resilience often emerges not from complex fixes, but from simplifying core assumptions. State coordination becomes critical when systems cannot be fully stateless. Databases, distributed caches, and consensus-driven services require mechanisms to maintain consistency across nodes. Quorum-based systems ensure that a majority of nodes agree before a decision is finalized, preventing split-brain conditions. Leader election assigns one node as the coordinator, responsible for orchestrating writes or updates. These mechanisms preserve correctness during failover, but can add latency and complexity. For example, in a distributed database, quorum ensures that data is not lost or corrupted even if some nodes go offline. The trade-off is slower performance compared to purely stateless models. Understanding these dynamics allows architects to balance the need for consistency with the need for availability, aligning technical design with business priorities. Replication strategies further illustrate the balance between consistency and performance. Synchronous replication ensures that data is written to multiple locations before confirming success, guaranteeing consistency but adding latency. Asynchronous replication writes locally first, then propagates updates later, reducing latency but risking data divergence in the event of failure. Both approaches have valid use cases. For example, financial systems often require synchronous replication to ensure transaction accuracy, while content delivery systems may rely on asynchronous replication for speed. These trade-offs echo the fundamental tension between immediacy and assurance. Choosing the right mode means considering not only technical constraints, but also user expectations, regulatory requirements, and tolerance for risk. Replication thus becomes a strategic decision, not just a technical setting. Consistency models define how users experience data during disruptions. Strong consistency ensures that once a write is confirmed, all users see the same result immediately. Eventual consistency, by contrast, allows temporary differences while updates propagate. This is acceptable for some applications, such as social media feeds, where slight delays are tolerable. For others, like banking transactions, consistency must be strong to maintain trust. The choice of model influences user-visible behavior during partitions or failovers. It also determines how resilient the system appears, as users may judge resilience by whether their data looks accurate and timely. By aligning consistency with application requirements, architects ensure that resilience supports not only uptime, but also correctness and trustworthiness. Idempotency is a principle that allows safe retries during recovery processes. An idempotent operation produces the same result whether executed once or multiple times. For example, processing a payment should be idempotent. If the system retries after a timeout, it must not charge the customer twice. Idempotency is crucial during failover, where retries may occur automatically as systems recover. Without it, recovery efforts could cause more harm than the original failure. Designing operations to be idempotent requires foresight, but pays dividends in reliability. It allows systems to recover gracefully without introducing duplicate actions, aligning with the broader goal of resilience, sustaining functionality even under imperfect conditions. Timeouts, retries, and exponential backoff are mechanisms that protect systems from cascading failures. Timeouts prevent one slow service from indefinitely tying up resources in another. Retries provide a chance for transient errors to resolve, while exponential backoff ensures that retries do not overwhelm recovering systems. This pattern reflects the principle of patience in engineering, trying again, but with restraint. Without these mechanisms, failures can propagate rapidly, as stuck processes consume resources and repeated retries create storms of traffic. By building in controlled timing, systems can ride out temporary issues without collapsing under pressure. These patterns demonstrate how small design choices and error handling can have outsized effects on overall resilience. Circuit breaker and bulkhead patterns isolate faults and prevent them from exhausting shared resources. A circuit breaker monitors interactions between services and temporarily halts requests if failures cross a threshold, giving the failing service time to recover. Bulkheads, named after ship design, compartmentalize resources so that a failure in one area does not sink the entire system. Together, these patterns prevent runaway failures from spreading unchecked. For example, a circuit breaker might block calls to a failing payment gateway, allowing the rest of the application to remain responsive. Bulkheads might allocate separate resource pools to different services, ensuring one misbehaving component cannot starve others. These strategies embody resilience through containment, preserving system stability even under stress. Finally, queue-based decoupling introduces buffers between services, absorbing bursts of activity and smoothing recovery. When one component fails or slows down, the queue holds requests until the system is ready to process them. This prevents cascading slowdowns and allows services to recover gracefully. For example, an order processing system might place incoming requests into a queue, ensuring they are not lost even if the processing service temporarily fails. Once it recovers, it resumes pulling from the queue at its own pace. Decoupling through queues transforms brittle chains of dependencies into flexible pipelines that can bend under strain. Combined with other resilience patterns, queuing makes complex systems more tolerant of real-world variability. Chaos engineering closes the loop by validating resilience assumptions through controlled experiments. Instead of waiting for failures to occur in production, teams intentionally introduce disruptions in non-production or carefully governed environments. These disruptions might simulate server crashes, network partitions, or latency spikes. By observing how systems respond, teams gain confidence in their designs and uncover weaknesses before real incidents expose them. Chaos engineering is like a stress test for infrastructure, revealing whether the system bends or breaks under pressure. While it must be practiced responsibly, it reinforces the idea that resilience is not theoretical. It is proven through practice, iteration, and continuous learning. By embracing controlled chaos, organizations ensure that their resilience strategies are not just aspirations, but demonstrated capabilities. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Service-level objectives, or SLOs, provide the measurable targets that define what resilience means in practice. Instead of vague promises of reliability, SLOs specify clear thresholds for performance and availability that align with user expectations. For example, an SLO might state that a service must be available 99.95% of the time over a given month, or that response times must remain under 300 milliseconds for 95% of requests. These targets are not arbitrary, they are negotiated commitments between engineering teams and the business. By establishing SLOs, organizations set realistic goals that drive design choices, operational practices, and investments in redundancy. Without them, resilience efforts risk drifting into either over-engineering or under-preparation. With them, teams have a compass that guides priorities and allows them to measure whether resilience strategies are actually delivering on their promises. Service Level Indicators, or SLIs, are the metrics that track whether systems are meeting their SLOs. Common SLIs include latency, availability, correctness, and saturation. Latency measures how quickly a system responds, availability tracks uptime, correctness ensures outputs are valid, and saturation gauges how close resources are to being overloaded. By monitoring these indicators, organizations gain the data needed to evaluate resilience in real time. For example, if latency begins to creep upward while saturation increases, it may signal that scaling is required before failures cascade. SLIs turn abstract objectives into actionable signals, forming the feedback loop that keeps systems aligned with expectations. In this way, SLIs are the pulse checks of resilience, continuously informing whether the patient is healthy, strained, or at risk of collapse. Recovery Time Objective, or RTO, and Recovery Point Objective, or RPO, define the boundaries for acceptable recovery during disruptions. RTO measures how quickly a service must be restored after an outage, while RPO measures how much data loss is acceptable, expressed in time. For example, an RTO of 1 hour means that operations must resume within 60 minutes, and an RPO of 15 minutes means no more than 15 minutes of data can be lost. These measures translate business needs into engineering requirements, shaping the choice of replication strategies, backup schedules, and failover mechanisms. They also highlight trade-offs. Tighter RTOs and RPOs demand more investment in redundancy and automation. By making these objectives explicit, organizations ensure that resilience efforts align with business tolerance for disruption and loss. Backup strategies remain a cornerstone of resilience, ensuring that data can be restored even after catastrophic failures. A comprehensive approach often blends full backups, which capture everything at a point in time, with incremental backups, which capture only changes since the last backup. Snapshots add another dimension, preserving quick recovery points with minimal overhead. The key is storing backups in protected locations, ideally isolated from primary systems to prevent corruption or ransomware from spreading. For instance, off-site or cross-account backups ensure independence, making them reliable when primary environments fail. Backups are more than just insurance. They are active enablers of recovery. Without them, even the most redundant systems can collapse irreversibly. With them, organizations gain a safety net that supports both short-term incidents and long-term continuity needs. Restore drills and game days validate that backup strategies and recovery processes work as intended. It is one thing to have backups and runbooks written down, and another to prove that they can be executed effectively under pressure. Game days simulate real incidents, such as a database corruption or a regional outage, and require teams to restore services within defined objectives. These exercises test not only technical mechanisms but also human processes, exposing gaps in documentation, communication, or coordination. The practice is like fire drills for buildings. They ensure readiness when the real emergency comes. Without such drills, organizations risk discovering critical weaknesses at the worst possible time. By rehearsing recovery, teams build muscle memory, confidence, and resilience that cannot be gained from theory alone. Multi-region deployment patterns extend resilience by spreading workloads across geographic boundaries. By running systems in more than one region, organizations protect against regional disasters while improving performance for global users. This may involve active-active deployments where multiple regions serve traffic simultaneously, or active-passive setups where one region remains on standby. Such designs raise important considerations about data sovereignty, latency, and quorum. For example, keeping user data within national borders may conflict with global replication goals, requiring careful design. Quorum rules determine how many regions must agree before transactions are confirmed, influencing both resilience and performance. These trade-offs illustrate the complexity of global resilience. While multi-region designs increase protection, they also demand sophisticated coordination and governance to avoid introducing new risks. DNS failover and traffic steering provide the agility to redirect user traffic rapidly during outages. If a primary region becomes unavailable, DNS can update records to point users to a standby site, often within minutes. More advanced traffic steering allows granular control, directing traffic based on latency, geography, or health checks. For example, a global service might automatically route European users to a European region unless it becomes unhealthy, in which case traffic shifts to another location. This dynamic capability ensures continuity without manual intervention, turning DNS from a static address book into a living system of resilience. The speed and precision of these mechanisms often determine how visible disruptions are to end users. When designed well, failover may happen so smoothly that customers never realize a problem occurred. Data resilience is about ensuring both availability and throughput, often using replicas, partitioning, and sharding. Replicas provide copies that sustain service even if one instance fails. Partitioning splits data across multiple nodes, distributing load and isolating failures. Sharding takes partitioning further, dividing data based on keys so that large datasets remain performant. These techniques allow systems to remain responsive and available even under stress. For example, a global messaging service may shard data by user ID, ensuring no single node becomes a bottleneck. The principle is distributing risk and load so that no single failure brings the system down. Data resilience mechanisms require careful tuning but offer one of the most powerful ways to scale availability alongside reliability, making them central to resilience engineering. Configuration parity and drift control ensure that standby environments are truly ready when activated. If backup systems are misconfigured or lagging behind production, failover will falter. Configuration parity means maintaining identical setups across primary and secondary environments, while drift control involves continuously monitoring and correcting any divergence. This is like keeping a spare tire properly inflated and checked. If neglected, it is useless when needed. Tools and automation now make it possible to enforce parity continuously, reducing human error. Drift control highlights a subtle but critical truth. Resilience depends not only on grand architecture but also on meticulous operational discipline. Without it, all the investment in redundancy may collapse under the weight of preventable mismatches. Capacity management and autoscaling policies preserve the headroom necessary for resilience during failovers or surges. If a system runs at near full capacity under normal conditions, it will have no room to absorb extra load when instances fail or traffic spikes. Capacity planning ensures there is slack in the system, while autoscaling automatically adjusts resources in response to demand. Together, they allow systems to bend rather than break under stress. For example, if one zone goes offline, autoscaling can spin up replacements in another, sustaining availability. The trade-off is cost, as maintaining headroom requires paying for unused or underused resources. Balancing this trade-off is a key part of resilience design, ensuring that systems are neither brittle from under-provisioning nor wasteful from over-provisioning. Dependency mapping and blast radius analysis identify which components are most critical and how failures could propagate. By mapping upstream and downstream services, teams can see which dependencies require the strongest protections. Blast radius analysis then considers how far the impact of a failure might spread, allowing designs to compartmentalize and contain disruptions. For example, if a payment service fails, how will that affect order processing, inventory, or customer notifications? Mapping this chain helps prioritize resilience investments where they matter most. It also highlights opportunities to decouple systems, reducing interdependence that magnifies risk. This perspective shifts resilience from a generic goal to a targeted discipline, ensuring resources are applied where they deliver the greatest impact. Runbooks and automation codify the steps required to recover, ensuring consistency and speed during crises. A runbook is essentially a recipe for failover, rollback, and verification. When automated, these steps can execute within seconds, minimizing downtime and reducing reliance on manual intervention. Automation reduces human error under pressure, but runbooks still serve as vital documentation for training and oversight. For example, an automated failover may switch databases between regions, while the runbook describes the verification checks administrators must perform afterward. Together, they provide both execution and assurance, turning recovery from an improvised scramble into a repeatable, reliable process. In resilience engineering, documentation and automation are not extras. They are core enablers of confidence. Observability tailored for resilience tracks key signals that indicate how systems behave under failure. Known as the golden signals, latency, traffic, errors, and saturation, these metrics allow teams to detect anomalies and correlate them with failure modes. Observability tools also provide traces and logs that help diagnose why a failover occurred and whether it succeeded. This visibility is essential for learning from incidents and improving future designs. Without it, resilience strategies operate in a vacuum, untested and unverified. Observability thus closes the loop between design and reality, ensuring that resilience is not assumed but demonstrated through data. By continuously measuring, analyzing, and refining, organizations can evolve resilience strategies alongside changing workloads and threats. Cost-risk trade-offs underline every resilience decision. More redundancy, broader replication, and faster failovers all improve continuity, but they also raise expenses. Organizations must balance the level of resilience against their budget and risk appetite. For example, an online gaming platform may accept occasional downtime for non-critical services but invest heavily in resilience for payment systems. The discipline lies in aligning resilience spending with business value, ensuring that protections are strongest where the stakes are highest. Blindly pursuing maximum uptime without regard for cost can drain resources, while underspending leaves systems fragile. By explicitly weighing cost against risk, organizations create resilience strategies that are not only technically sound but also sustainable in the long term. For learners, the exam relevance lies in recognizing which patterns best meet uptime, integrity, and recovery commitments. Questions may ask you to distinguish between active-active and active-passive topologies, or to apply RTO and RPO requirements to backup strategies. More broadly, this knowledge equips you to design real-world systems that balance user expectations with operational realities. Resilience is not about eliminating failure, but about engineering systems that recover predictably and quickly when failure occurs. By mastering these concepts, you develop the ability to choose and justify resilience patterns that deliver continuity under pressure, preparing you for both certification and practice. In summary, Resilience emerges from deliberate patterns, measurable targets, and verified recovery execution. High availability keeps systems running through routine faults, while disaster recovery provides safety against catastrophic events. Patterns such as redundancy, quorum, circuit breakers, and queues create structures that bend instead of breaking. Objectives like SLOs, RTOs, and RPOs translate business expectations into engineering requirements. Continuous drills, observability, and cost-aware trade-offs ensure resilience remains both effective and sustainable. Together, these practices form a comprehensive discipline that transforms failure from a crippling event into a manageable challenge. By embedding resilience into design, organizations safeguard trust, sustain operations, and demonstrate maturity in the face of inevitable disruptions. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.